Hello there, Mr. Sutton here, bringing you this lesson on integration with respect to the y-axis. Specifically, we are going to be solving area and volume problems using integration with respect to y. So let's talk a little bit about integration with respect to y. First off, to review what we've been doing so far. Thus far, we've been integrating with respect to x, which means we're adding vertical distances together. You've got a bunch of super skinny rectangles and added them together left to right. In this lesson, we're going to be integrating with respect to y, which is to say we're going to be integrating sideways based on horizontal distance. So let's say that we have some bounded region with two functions, and instead of having vertical rectangles that we're adding together, you're doing horizontal rectangles. To compare this with integration with respect to x, the old way of doing things, x integration, you have an integral that is going from the leftmost x value to the rightmost. We're going left to right on the bounded region. And we're doing top function minus bottom function, upper function minus lower function. And since this is a function of x that we're integrating on this, dx was our differential in this situation. Now, y integration changes all of this, and you kind of have to turn your head sideways to really appreciate this. With y integration, you're not going from left to right anymore. You're going from lower y values to higher y values, which is to say you're going from bottom to top, from lowest to highest y values. And you can't really do upper minus lower anymore because y integration is doing things horizontally in terms of what we're adding together. So now we need to do rightmost function minus leftmost function. And since we're integrating with respect to y, our differential is going to be dy instead of dx. In fact, if you take a look at this graph a little more closely, look at this, g of y, f of y. These are both functions that take y as an input and x as the output. So that's how we're changing things today. So now let's see how this sideways integration stuff works in practice. So we're going to find the area between these functions here. Let me take a sec to graph these out. So I've got these in my y equals. I do zoom 6 on these, and I get my square root and my line, and I could zoom in a little bit more if I wanted to, and we have this bounded region in here. Now, the way we would normally do this would be just go from left to right, so from 0 to 4, and integrate with top minus bottom kind of reasoning. The trouble is here that the top function is the same, but the bottom functions are not. Like from 0 to 2, your bottom function is just the x-axis, and after that, it's this line x minus 2. So this is actually going to require two integrals when integrating vertically with respect to x, because again, we have this function change at x equals 2. But now if we think about integrating this from bottom to top going sideways, there's only one integral if you're thinking about this in terms of rightmost versus leftmost function. So we can do this in one integral if we do it with respect to y. Here's the catch though. You need to express the functions in terms of y first. These are functions in terms of x. So to get them in terms of y, all you really have to do is just solve for x in terms of y. So right here, to get x by itself, we could just square both sides, and that would give us y squared over here. Now, I could call this x equals y squared, but it'd be fancier to call it f of y equals y squared. Just like instead of writing y equals radical x, we write f of x equals radical x. For this next one, if I add 2 to the other side, well, now I've got f of y equals y plus 2. So we're going to use these functions in an integral to figure out this area. The other thing we need, though, is the limits of integration. Remember, we have to go from bottom to top with this kind of integration. At the bottom, we definitely have 0. It's the x-axis. But how about the top? How can we find the intersection for this y value for f of y equals g of y? The safest way to do it is just to take what you already have on your grapher and take the y value out of that. So on my graphing calculator, I'm just going to do second trace, intersect, and I'm going to go over here and press enter 3 times, enter, enter, enter. Now normally I'd be interested in the x value, but this time around I want the y value, which they also give us. They told us that's 2. So now I'm going to have an integral when I'm finding this area from 0 to 2 of, well, I have to do right minus left at this point. So that's going to be g of y minus f of y, and then don't forget we have a dy in this one because we're integrating with respect to y. Let me put this in the calculator now. So I've got math 9, integral from 0 to 2, And at this point, what do I do? Because everything here is in terms of y. So the good news is, as long as you're consistent with how you use the letters, your calculator doesn't really care what letter you have in there. So you can actually use x and dx on your calculator as long as it perfectly mimics what you're doing on paper in terms of y. So I want to do g of y. I'm just going to write that as x plus 2. I want to subtract f of y. So I'm going to subtract x squared. And over here, I'm going to put a dx. Enter, and that gives us 3.333. For this next problem, we're going to step it up to find some volume. Specifically, we're going to take the area between x squared and 4 in the first quadrant and revolve that around the y-axis. This is a no calculator problem, so take a minute to graph out this situation. All right, so we have a parabola and y equals 4, and we've got just the first quadrant area. We're revolving that around the y-axis now. Since we're going around a vertical axis of revolution, now your radius, as you go up these y values, your radius has to be really an x value, an x distance. So with that in mind, pause the video and see if you can figure out how to modify your normal procedure for doing this. All right, so since our radius is taking a y value as an input and giving you back an x value, we need to rewrite this function in terms of y. So I can square root both sides to get x by itself. That's just going to be f of y equals the square root of y. And this is what I'll use in my area formula. Now let's find the area formula for my cross-sections. What kind of cross-section should we have? Since my axis of revolution is one of the boundaries for my bounded region here, I can just use disks. There's no space in between when I revolve this. So I'm going to write a of y equals pi r squared. Note I'm doing this as a function of y. What's my radius going to be? It's just the distance from the axis of revolution to the end of the boundary here, which is just given by the square root of y. It's just giving us back an x value. So I'm going to write this as pi times radical y squared. Now to write my integral, so I'm going to have the volume equaling the integral from bottom to top, remember, so 0 to 4 of, and I'm going to simplify this now to be just pi y, and don't forget the dy. Doing this by hand, so we need an antiderivative. That's going to be, let's see, this bumps up to an exponent of 2, so we have 1/2 pi y squared, or pi over 2 y squared, evaluated from 0 to 2. To make my life a little easier, I'm going to yank out this pi over 2, and inside I'm going to have 4 squared minus 0 squared. So this is just going to be, let's see, pi over 2 times 16, which is pi, or just going to be 8 pi. For this next problem, we want to write but not evaluate an integral for the volume of the bounded region from these functions revolved around x equals 5. So right away, we kind of hit a snag because these are all expressed in terms of y already. So although we're allowed to use a calculator on this problem, how do we even graph these things? So here's a little trick. To draw things in this form, x equals f of y form, we're going to put the functions in terms of x, and we're going to put them into the draw inverse function on our calculator, which is just second program, which is the draw menu, and then option 8. So here's what it looks like when you enter it in the calculator. I'm going to do draw inverse of square root of x over 2. And that's going to draw the inverse of x over 2, which is going to be the square root of y over 2. Then I'm going to do draw inverse of square root of x for this other one. So let me show you on the calculator what that looks like. So the first thing I'm going to do on this problem before I even do this is I'm going to go to y equals and put in the horizontal line y equals 4 because, well, why not? Zoom 6 that thing. We've got a horizontal line. No shocker there. Let me quit out of here now, and I'm going to do second program. That gives me my draw menu. Down here, option 8 is the draw inverse option, and now I'm going to put in what I have here. So draw inverse of radical x over 2 gives me this function here, and if I quit out, I'm going to just yank that input from before because it's pretty close to what I need. Delete the 2 and the divided by fraction bar, enter again. There is the inverse of radical x. So this is a visual of what I'm dealing with. I've got this shaded region in here, and now I want to revolve that around the line x equals 5. That's a vertical line at x equals 5. So you might be thinking, well, if I want to revolve around this, there's a big space in between my axis of revolution and my bounded region. So I'm going to need washers. And if you're thinking that, why, you would be correct. So pause the video and see if you can write the integral that uses washers to find that volume. All right, so if I'm using washers, I'm going to write this as a of y equals pi times big R squared minus little r squared. For my big R, that's going to be the distance from the axis of revolution to the further away part of the curve. And now keep in mind, again, these are left-right distances. So that's going to be for big R 5 minus whatever this first function was. It was actually f of y. So we're doing 5 minus f of y squared. Still have a pi out there. Next, for my little r, I'm going to have 5 minus the closer function, 5 minus g of y squared. And I have to actually write an integral for the volume. This isn't quite there yet. So for my volume, I've got the integral from 0 for the y value to 4 of, well, a of y dy, because I already wrote all that out. For our last problem, we're given the base of a solid is the region enclosed by f of y and g of y here. And our cross-section's perpendicular to the y-axis now. This tells us we have y integration, our squares. Find the volume with a calculator. All right, well, pause the video and get as far as you can on this one before you hit a snag. So for my part, I'm going to graph this as soon as I can. Now, I'm going to be a little bit clever about how I graph these. I'm actually going to put these in my y equals in terms of x. I'm going to need them in there later anyway for another reason. But for now, I can actually do draw inverse a little quicker if I just do alpha trace y1 and y2 in draw inverse. But first, I'm going to deselect these. I don't really want to draw the original right side up graphs. I just want to draw the sideways versions. So second draw, option 8, draw inverse. Let me do alpha trace y1. There's my sideways parabola. And then quitting out of there and doing draw inverse on alpha trace y2. There's my line, which is also just a line. So I have this bounded region that I now want to get some squares and find the volume of those squares. So now the squares, we have an area formula of a of y equals s squared. The base of the squares, since these squares are now kind of left-right squares rising out of this bounded region, I'm going to be doing right minus left to figure out the base. So I'm going to be doing, let's see, that's going to be the f function minus the g function, which we're going to square. Now I also need intersections. We're going from bottom to top. And the trouble with what we've done on our calculator, if you wanted to use it to find those intersections, is we can't actually trace anything. Like if you try pressing trace, nothing's going to happen because this is just a picture. It's not an actual function in the calculator. So what I'm going to do to work around that is I'm going to graph these in terms of x. To find intersections, you have to graph things in terms of x. So on the calculator, I'm going to go ahead and quit out of here. I'm actually going to go back to my draw menu and clear draw, option 1, just so I don't have that stuff clogging up the works. And then I'm just going to do zoom 6. Actually, before I do that, let me go to y equals and reselect my functions. So these were the originals here with x in them. Now let me do zoom 6. And now I'm going to find out where these things intersect. So you might be saying, well, I'm going to be figuring out x values where they intersect. And that's true. But the x values you find here for the intersections, all the x values on those f of x graphs you're doing right now, those are really just y values on this graph over here. So let's go back then and find those intersections. So if I do alpha trace, option 5, intersection over on the left here, enter, enter, enter. That's -3 for the x, so that really corresponds to a y value of -3 down here. And then if I do second trace, option 5, and go over to the other intersection, enter, enter, enter. Well, that's now x equals 2 for this graph. That means we really have y equals 2 for this graph here. So I see that I've got, when I set f of y and g of y equal to each other, I have y values of -3 and 2 where these actually intersect. So now I've got my limits. I've got my function to integrate. Let's go ahead and integrate. I can say my volume is going to be the integral from -3 to 2 of this area function up here. But now I have to actually do it on the calculator. So my first step to doing this, because I like to do a lot of work in the y equals, is actually put my area function in the y equals. So y1 minus y2 squared, that's this function minus this function in here. Now, the nice thing is that when you integrate with respect to y in your calculator, it's going to figure out how to make all these y values. So quitting out of there, I'm doing Math 9, integral from -3 to +2. Now I'm just going to do alpha trace, and y3 was where I put that area function. And I'll do dx. Since all my functions in here are in terms of x, I'm going to make x the differential. But it's really in terms of y on paper. So this comes out to 104.167. So that's it for y integration. In our next lesson, we'll integrate with respect to the z-axis. Haha, just kidding. Till next time, Mr. Sutton signing off.